All right, hello everyone. My name is Cole Juracek. I am a graduate from the Masters in Statistics program, class of 2021. Dr. Goons has requested that I go ahead and give an example of my master's completion project. I chose to do the portfolio of work. So I'm going to go ahead and share the poster that I've done, as well as hopefully provide an example of the speech that may be useful for you all in the future. I'm not going to be super strict on the time requirements as I was when I was presenting, and I might just be a little bit more informal, but hopefully this should serve as a good reference. So give me just a sec here. Let me share the screen. All right, I hope that looks good. Okay, so this is the portfolio of work that I've done for my completion project. This poster is going to consist of two projects that I've worked on over the 2 years when I was a master's student at Duke. So on the left, I have a project that I worked on in the summer of 2020 as a data science internet proof points, which is a cybersecurity company. And on the right-hand side, I have the final project that I worked on for Stat 663. I don't know if you all are taking that, but that is basically the second computing course in the statistics master's program. So I did this project with Pierre Gardin, who was another master's student at the time. And so despite the poster's name, I'm actually going to be presenting pretty much primarily on the project that is on the right-hand side of this poster presentation. And also I might go through some of the, bells and whistles that I was trying to do when presenting, just to, keep this as realistic as possible. So without further ado, I'll just get right into it. So starting things off, we have the latent Dirichlet allocation, or LDA model, which I'll be referring to from this point forward. So what is it? Well, it is a generative probabilistic model for discrete data, and almost always this is going to be text-based data. So first, I'm going to go ahead and explain how the model works, including all of the parameters and the generative process for how the data is being created. We'll then go ahead and perform inference on these parameters using what's known as a collapsed Gibbs sampler. And here we are basing this algorithm off of a paper called Fast Collapsed Gibbs Sampling by Ian Porteous and his group. And then finally, I'll go ahead and discuss the results of running our algorithm on an example data set. So when explaining the model, I'm pretty much going to be primarily referring to the plate notation that we have, as well as the table right under methods. So with LDA, we start with a corpus of capital D documents, as well as the desire to find capital K underlying or latent topics within them. And in LDA, when we refer to a topic, all this is simply a distribution over words in our vocabulary. And to get a sense of what a topic is about, or how we make sense of a topic, we look at the words in a topic that have high probability, and hopefully these words are related to each other in some meaningful way. So these topics are described by the K-phi vectors that we have in the bottom left of the plate notation. So now that we've defined a topic, we're going to go ahead and move on to documents, which is this outermost box on the right side of the plate notation. In LDA, we assume that each document is what's known as a mixture over topics. So for instance, we can think of a given document as maybe 20% from topic 1, 70% from topic 2, and 10% from topic 3. So basically just a series of percentages of topics that a document is about that add up to 100%. And we describe basically this notion, which is given by theta in the plate notation. So every document gets its own topic mixture weights. After this, we move on to Z in the plate notation, which is the inner box on the right. So Z is the topic assignment for a given word in a document. The frequency with which a word belongs to a specific topic actually follows directly from the value of theta, in that if the weight for topic 1 is 0.7, then that means we expect roughly 70% of the words in the document to belong to topic 1. If we want to get a little more technical and kind of make this concrete, we go ahead and assume that all of the latent topics, all of the Z's for the words, are drawn all at once from a multinomial distribution, and the event probabilities for this multinomial are given exactly by the mixture weights of theta. So that is how those two elements are related to each other. And then finally, we actually have the words themselves, the W here, and that is actually the only part of this process that we observe. So everything else is latent. We're assuming this generative process on it, and we're going to try and do inference on these parameters. But as this is a Bayesian model, we need to go ahead and specify priors on the top level parameters. And that is what these alpha and beta values are here. They are the hyperparameters for our prior distribution. So in our case, the prior distribution are going to be the Dirichlet distributions. And that is where the LDA name comes from, the Dirichlet. So we go ahead and place Dirichlet priors on the topic distributions per document, theta, as well as the word distributions per topic, phi. And so the magnitude of these Dirichlet parameters is going to go ahead and affect how sparse the corresponding distributions are going to be. In the case of the document topics, the thetas, for instance, a small value of alpha is going to encourage documents to consist of a small number of topics. So essentially, we don't think documents are about a blend of topics. Whereas larger values of alpha, as alpha grows to infinity, we're essentially suggesting that each document is going to be almost a complete blend of every single topic there. So equally about topic 1 as topic 2, et cetera, et cetera. And the same logic here applies to the word mixtures per topics as well. And so with this, we have the following generative process for our model, which is given on this right-hand side here as well. So first, we go ahead and draw the topic mixtures for each of our documents and the word mixtures for each of our topics. As previously stated, these are determined by the Dirichlet priors with alpha and beta hyperparameters respectively. We then go ahead and draw the set of latent topics for each word in a document. And we model this as a multinomial distribution with probabilities given by the previously drawn theta values. And then finally, once a word's topic is fixed, we simply index into the appropriate topic distribution and draw it as a categorical draw from that. So basically just a weighted draw from a given distribution. So with all of that being defined, we're going to go ahead and move on to the method section, or essentially what we're trying to do with this. So for LDA, as with most Bayesian models, of course, we'd like to compute or kind of get at the posterior distribution of all of these latent parameters here. So the ph's, the thetas, and the z's, given the observed data or all of the words in our documents. However, the posterior for this hierarchical model is extremely complicated. It's going to consist of all k phi values, all d theta values, and a z parameter essentially for every single word in the document. So conceivably, this joint distribution for the posterior consists of hundreds of parameters. So kind of tricky to get at and certainly not possible to write down explicitly. As for how we actually obtain this posterior distribution, we actually could use traditional Gibbs sampling with regular full conditionals for each variable. And the authors actually claim this does work. However, they also claim that this MCMC Gibbs sampler is not going to mix in any reasonable amount of time. So basically, it's just going to take too long to start obtaining samples or draws from this full posterior distribution. So thus, the solution to this, or one proposed solution at least, is we're going to go ahead and create what's known as a collapsed Gibbs sampler. And this is going to go ahead and help speed things up a little bit. So the goal here is to create a Gibbs sampler for only the marginal posterior of the latent topics z. So we're interested in getting at only the probability of z, or all of the latent topics, given the words w. So to create a Gibbs sampler, we first need to obtain a marginal joint distribution of the latent topics z and the words w, which is given by this top equation up here. And one of the properties, of course, for marginal distributions, or obtaining them rather, we achieve this by integrating the full joint distribution, which we have explicitly written out here, which follows from this plate notation. We integrate this over the range of thetas and the range of the phis. And while simplifying this is actually really involved, it's not even shown in the paper. However, it is shown on the Wikipedia article for latent Dirichlet allocation if you're interested in checking it out. It basically consists of breaking apart the thetas and the phis into separate integrals because they're independent, and adding appropriate normalizing terms to get these integrals to recognize as a Dirichlet distribution such that they integrate to one and kind of drop out. So again, pretty involved, not worth showing here, but you can go ahead and check that out if you'd like to see it. But as for now, we'll just go ahead and assume that we have this distribution, and we'll proceed from here. So with this distribution, we can go ahead and proceed with making a Gibbs sampler on just the latent topic Z, which is given by this second set of equations right here. So we create this Gibbs sampler via full conditionals on a single topic Z sub ij, condition on all of the other latent topics, as well as the words themselves. We see the probability of a word being assigned to a topic K consists of two terms pretty much. So the first term, the A term, this encourages what I call topic homogeneity within the documents. And what this means is that all else being equal, a new word has a higher chance of being assigned to topic K if topic K appears a lot in that document. And the second term, the B term, this encourages word homogeneity in topics. So all else being equal, a new word has a higher chance of being assigned to a given topic if that word frequently shows up in a topic. So to kind of crystallize this and make this concrete, essentially if the word baseball belongs to topic 1 50 times and belongs to the remaining topics, let's say 5 times, then a new instance of the word baseball is very likely to be assigned to topic 1 as well. And so once we understand this formula, we can actually move on to the algorithm for the Gibbs sampler on the left. It's actually pretty straightforward, but the biggest drawback to it is its time complexity. But luckily, the algorithm is able to produce pretty coherent and reasonable topics within a short amount of iterations. We actually just ran ours for 15 iterations, and we were able to get at least decent results. Somewhat hard, just as an aside, to evaluate the results of latent Dirichlet allocation, as it is an unsupervised method, so you can't just kind of quantify it with cross-validation. It's a little more tricky to get at. So just to briefly run through this algorithm here, starting on line 2, this is the outermost loop that controls the length of the Markov chain for each latent topic. And then moving on to the second and the third loops, this simply iterates over every latent topic in every document. And then finally on lines 5 through 11, we get to actually calculating the topic probabilities for a given word using these formulas described here on the right. And then once we've run the sampler for long enough, we can start to think of these draws for the latent topics as draws from the marginal posterior distribution. And we can go ahead and conclude the final topic as the mode of this discrete chain. Once we have this, we can go ahead and recover estimates of the per document topic mixture weights theta here, as well as the per topic word distributions phi, which are given in the bottom right here. And so once we have done this, we've pretty much approximately gotten at the full posterior distribution for our LDA model. Moving on to the application here, now that we have the posterior quantities of LDA, what do we actually do with them? And as previously alluded to, the most immediate application for LDA is kind of exploring the corpus, seeing what our collection of documents is about, whatever that means, or just generally summarizing our collection of documents, which we more or less get from our LDA model without really needing to do any extra work on our end. So that's very nice. To that end, we have implemented LDA on 2 data sets. We've only shown the results of one here just for brevity. So just to give a brief description of these data sets, the first one that we worked with and what we'll be showing is what's known as the 20 news groups data set. And the other data set that we worked with is a set of news headlines from Reuters. And while the former was collected in such a way that the number of topics should probably be set equal to 20, we should probably try to find 20 topics. The latter does not really have an immediate notion of how many topics we should try to find. And I suppose here I'll just mention that the value of the topics we're trying to find, K, this is actually a hyperparameter for this algorithm. It's something you as the modeler choose, and there's not necessarily a correct answer for it. It just depends on the objective you're trying to achieve. You can think of it as choosing the number of clusters in a clustering algorithm, for instance. So just some quick processing on the left here before we ran the LDA algorithm, just some standard pre-processing such as tokenizing, removing stop words like of and ands that are just noise. And finally, we lemmatized each token so that way we kind of normalize verb tenses and plurals. So after this, we ran our algorithm with parameters recommended by Porteous that you can find in the paper, as well as 15 iterations. So after we ran this, we can look at some of the results, which the first one we have here is given in this table. The first way we can get at exploring it is to look at words within a topic that have high probability. So the table in the middle contains the top 5 words with highest posterior probability in 3 select topics that we found. The left column is a strictly subjective assignment of these words to what we thought the topic would be about. And in the middle, we tried to match it to one of the 20 news groups the data was pulled from. But again, this was subjective as well. And some of the news group topics tend to overlap with each other. So there's not, again, really a right or wrong answer. This is just how we as modelers interpreted it. So we can observe the results of LDA actually finding coherent topics, as most all of the words here are related to both each other and the predetermined topic that we thought it was about. Taking another look at it, kind of another angle we can try to approach it from. On the right here, the very bottom right, we observe a graph of the posterior topic weights for a selected document, which is given in the caption down here. Quick note, while there should actually be 20 bars here for the 20 topics, I have plotted only the 3 highest weights strictly for visualization purposes, just to kind of declutter the screen. And in addition to that, the remaining topics actually had values close to 0 anyway. So we see the document is very much related to cryptography. It contains some keywords such as RSA, keys, algorithm, things of that nature, which our sampler has correctly identified as it has placed a large mass on the appropriate topic, the computer cryptography topic. We also observe this document here is pretty one-dimensional. It doesn't really seem to be about a blend of topics so much, and this is reflected by the low topic weights we found in the remaining topics. So in conclusion, I feel like learning this model and implementing it was really a culmination of many of the ideas that we've learned in this master's program. For instance, Gibbs samplers, hierarchical modeling, and especially trying to parse and implement ideas from an academic paper. And that's pretty much all I have to say about this poster and this presentation. I'd like to thank Dr. Goons again for reaching out to do this video presentation, and hope this is useful for anyone in the future. Thanks.